In today's lecture, we shall study about second law of thermodynamics and concept of entropy. As we know that the first law of thermodynamics is based on the principle of conservation of energy. It is the result of wide range of experiences that can be expressed as the total internal energy of an isolated system remains constant, though it may change from one form to another. It is then considered to be the basic law of nature and was named the first law of thermodynamics. The first law of thermodynamics was stated for the first time by Mayer and Helmholtz in Germany, and later by Joule in England and by Koldin in Denmark. The first law of thermodynamics has given us two important state functions, that is internal energy and enthalpy. As useful as it is, it also suffers from following limitations. This law fails to tell us the source of heat and direction of flow of heat. It does not define the ease or extent of convertibility of one form of energy into another form. It fails to explain why natural process or spontaneous process are unidirectional, that is, it proceeds only in one direction. For example, cooling down of hot tea, flow of water from higher level to lower level. This law cannot explain why all naturally occurring processes always tends to change spontaneously in the direction which leads to equilibrium. It does not say whether heat change is endothermic or exothermic. Work can be completely transformed into heat, but heat cannot be completely converted into work without causing permanent change in system or surrounding was not explained by this law. Hence, a need for another law of thermodynamics was necessary. The second law of thermodynamics forms the basis of predicting whether the particular reaction can occur or not, and if it occurs, then to what extent. Second law of thermodynamics may be stated in a great variety of ways. First is Clausius or Kelvin statement of second law of thermodynamics. According to this, it is impossible to construct a heat engine which will continuously abstract heat from a single body and convert the whole of it into work without leaving changes in the working system. Second is Planck statement. It is impossible to construct a machine operating in cycles that will convert heat into work without producing any changes in the surrounding. Third is Thomson statement. According to this, all natural or spontaneous processes tends to go to a state of equilibrium. Next is heat cannot itself flow from a colder body to a hotter body without the intervention of an outside agency. Any change favors a direction that leads to a greater chaotic dispersal of total energy of isolated system. Here we introduce another thermodynamic function, that is entropy, which is a measure of disordered form of energy. Now we shall study about entropy. We know that all spontaneous processes are associated with an increase in disorder, and the disorder of a system is expressed in terms of a function called entropy of a system. So entropy of a system is the measure of disorder or randomness of system. We can say that greater the disorder of the system, greater is the entropy, and more ordered the system, smaller is the entropy. Like the internal energy of a system, entropy is a property that depends only upon the state of the system. So we can say that it is a state function. An entropy change ds is generally defined as the entropy change for an infinitesimal reversible process is equal to heat absorbed reversibly divided by the absolute temperature. And for the finite change, the entropy change can be obtained by integrating the equation ds equals to dq reversible by t by applying limit of initial and final state. Thus, difference in entropy between two states can be calculated if the system is changed reversibly from one state to another. When heat is absorbed by the system, we say that Q is positive and temperature T is always positive. Therefore, the entropy changes delta S would also be positive. And when heat is rejected by the system, Q is negative and hence delta S also becomes negative. In case of adiabatic process, no heat is evolved or absorbed. Therefore, such changes occurs with constant entropy, and these changes are called isoentropic changes. Entropy is an extensive property. If S denotes entropy of 1 mole of the system, then for n moles the entropy of the system would be n into S. The unit for entropy is joule per Kelvin or joule per Kelvin per mole. Next is physical significance of entropy. The following aspects provide a definite physical significance of entropy. So first is entropy and unavailable energy. We know that energy can be converted into work, but all energy cannot be converted into work. So any kind of energy which can be converted into useful work is called available energy, and the energy which cannot be converted into useful work is called as unavailable energy. And entropy is the measure of this unavailable energy. In fact, we can regard entropy as unavailable energy per unit temperature, or the entropy into temperature is equal to unavailable energy. So over here we can say that entropy is directly proportional to unavailable energy. We know that natural processes are generally spontaneous, in which the unavailable energy goes on increasing, and this spontaneous process come to an end when the state of equilibrium is attained. In that case, the entropy is maximum. Hence, it is said that nature is trying to attain the state of maximum entropy. Next is entropy is the measure of disorder or randomness of the molecule of system. If we consider the transition from solid to liquid and liquid to vapor, then in solid state there is no freedom of translational motion. That is, there is order in the molecules of system. But when the solid melts, the molecule become mobile and degree of orderliness decreases. In vapor state, the orderliness is destroyed as the molecule enjoy the great degree of freedom. Thus, we can say that disorder is maximum in vapor state and entropy too is maximum. If we consider the condensation of vapor to liquid and liquid on freezing becomes solid by decreasing the temperature. In this case, the orderliness of molecule increases. At absolute zero, the disorder completely disappears or absolute order prevails. That is, entropy of solid will be zero. Next is entropy and thermodynamic probability. For all spontaneous processes, a change for less probable state to more probable state take place. Therefore, there will be increase in disorder and hence increase in entropy of the system. We know that entropy increases for all spontaneous processes. Hence, it can be said that entropy is the function of the probability of the thermodynamic state. Boltzmann gave the relation between entropy and the thermodynamic probability W as S equals to K ln of W plus C, where K is Boltzmann constant and C is also constant. Planck showed that C is equal to 0. Hence, S equals to K ln of W. This equation is known as Boltzmann-Planck equation, where W is defined as the ratio of probability in a given thermodynamic state to the probability in ideal thermodynamic state. Now, let's recall the characteristics of entropy which we have discussed earlier. Entropy is a state function. Entropy is an extensive property because for n moles, the total entropy of the system is n into S. The unit of entropy is joule per Kelvin. The sign of entropy depends on Q. When heat is rejected by the system, Q is negative and hence delta S too becomes negative. And the entropy increases when delta S is positive and decreases when it is negative. For adiabatic changes, no heat is evolved or absorbed. Therefore, such changes occurs with constant entropy and are called as isoentropic changes. Molar entropy is an intensive property and its unit can be joule per Kelvin per mole.